Hey everyone. In this video, I'm going to introduce regression models for count data. Okay, and so in count data regression, what we usually have for each unit, for each observation, is some kind of setting. So this could be either a spatial location or a time interval, and within each of these time intervals, we observe a certain number of events. Okay, so in that sense, it is different from the binomial model or the logistic binomial that we talked about and is also discussed in the textbook, where we have a defined set number of trials and we observe the number of successes, right? When we have count data, we don't really think of it as successes out of a certain set number of trials, but we just count the overall number of events that appear given a certain rate, okay, either over time or in a given region, okay. So it's slightly different from like the binomial distribution or the binomial or logistic binomial model, in the sense that we don't have this set, total number of trials, but we still, observe a number of events, so to speak. Okay. Um, of course, there are a lot of applications in political science, in different substantive areas that have outcomes that can be described as count data. For example, if you think about like conflict studies and you're trying to model the number of number of terrorist attacks, for example, in a conflict, in a civil war, that could be for each time period, it could be modeled as count data. You could also think about like legislative bills that are passed over a certain time period as count data, for example. So there are plenty of outcomes in political science that are ultimately can be represented as counts. Okay, and so similar to the way we talked about in linear regression or logistic regression, the variation in y in these numbers of or in these counts of events can be explained with a linear combination of predictors. Okay, so we have again, just like with linear regression or logistic regression, we have a set of predictors in our X matrix, and we have a set of coefficients that ultimately tell us something about the association between our predictors and the outcome measure, which is this count. The only thing that is different, again going back to our discussion of generalized linear models that we just talked about, is that now we have a different link function, okay, and we have a different data distribution. But other than that, it's still kind of within the realm of these generalized linear models, okay. So the kind of most standard way of modeling any type of count data is using a Poisson regression and basically assuming a Poisson distribution for the outcome variable. Okay, so the data distribution is therefore a Poisson distribution. We don't have to look at the exact specification, but just know that the outcome of that Poisson process is always positive, a number of successes or number of events essentially. Okay, and then we have our systematic component. And again, we need a link function similar to the logistic regression, but the link function that we're using here is basically the exponent. So we take e to the power of x times beta in order for our linear predictor to be strictly positive. Okay, so if we take e to the power of x times beta, we always have a positive linear predictor, and this positive linear predictor is then ultimately the parameter that is basically passed into the Poisson distribution. The Poisson distribution in general only has one parameter, lambda, which is equal to the expectation as well as the variance of that random variable. Okay, so in order to kind of just visualize what this could look like, we just simulate some fake data here with one individual predictor that is just drawn from a random uniform distribution, 100 observations ranging between -2 and 2, and then we take random draws from a Poisson distribution with our Poisson with again 100 draws, and the lambda parameter that I just mentioned is equal to the exponent of 1 plus 2 times x. Okay, so we're basically plugging in our systematic component as well as the link function right away. We're plugging in our predictor x that is drawn from the random uniform, or from the uniform distribution, and we have an intercept of 1 and a coefficient for x that is equal to 2. Okay, so that's our true data generating process. And we're going to estimate a few models in a second based on this fake data. Okay. The first thing we can do is we can directly plot the data based on this data generating process using ggplot. Of course, we plot both the actual simulated data points as well as the true function that is kind of that the data generating process is based upon. Again, this is just the exponent of 1 plus 2 times x. Okay, and that should be the expectation of our Poisson process conditional on x, basically. Okay. If we run this, we see that we have a clear kind of exponential curve here with increasing x. We have an increasing number of events in y. Okay, and the line that we fit through here is basically this exponential curve that we fit here, 1 plus 2 times x. Okay. So this is now simulated data from the Poisson regression. Suppose now we, of course, just have these data and we didn't know the underlying data generating process. Now, how can we kind of fit this this line through this data? Okay, there are two different ways that we can two different ways of how we can estimate these models in R. Okay, basically similar to our previous discussions, we talked about linear regression and logistic regression, both from a Bayesian perspective using Stan, as well as using kind of basic frequentist methods. And I'm just going to show you both, also because some of you had computational issues sometimes with the Stan models to estimate. So I'll show you both alternatives going forward, and you can kind of go back and forth depending on if you have issues with the Stan models, with the Bayesian estimation. Okay, in order to estimate a Stan or Poisson regression in Stan, we use our Stan GLM. Since this is a generalized linear model, we have this is now just based on our fake simulated data. Y is our outcome, X is our predictor. The only thing we basically have to change is that we have to specify that this the data distribution is a Poisson and our link is a log. Okay, so we use the exponent here, but basically kind of the inverse of that, of course, is the logarithm. So log of y is equal to, or the expectation of log of y is equal to x times beta. So similar to similar to how we talk about the inverse logit function as the link function for the logistic regression. Here we talk about the log as the link function for the Poisson regression, despite the fact that we kind of take e to the power of x times beta. Okay, so that's why the link here is the log. The data, as we said, is the simulated data, and refresh equals 0, so we don't have our Stan output during the estimation as part of this our markdown file. Okay, we can also do this without Stan. We can do this using the basic GLM command. The command is fairly similar. We have our model formula. We have our family equals Poisson. Here we don't need to specify the link function. It basically by default automatically knows that if we have a Poisson regression, then automatically this link function is passed through the exponent, basically, or the linear predictor is passed through the exponent, essentially. Okay. The output for the Bayesian estimation here is, we can see here, you can If you run the code on RStudio Cloud, you can also compare this to the basic frequent estimation. You'll see that, you know, with the default priors, the results are basically the same. We get our intercept, which is equal to 1, and our x coefficient, which is equal to 1.98 or just about 2, basically. So we recover the true data generating process that we specified here in our simulation with this basic toy example, right? So this is the basic framework. This is as simple as it is to just run a Poisson regression, either using Stan or using just the basic GLM function. Of course, there are some complications. One issue that is usually that we often encounter when working with count data is what is called overdispersion. Okay, and I mentioned briefly earlier in this video that the Poisson distribution only has one parameter, and this parameter lambda is equal to both the expectation and the variance conditional on x. Right. So this implies that the Poisson distribution basically always assumes that the expectation or the variance is equal to the expectation of the Poisson. Okay, and this is a fairly restrictive assumption, and we might have cases where basically the variance increases or decreases or is not equal to or is larger or smaller than the expectation. Okay, and so in order to kind of see what exactly this would look like, we have an additional parameter phi that basically can introduce additional variation or less variation for conditional on x. Okay, so here in the middle, in the center, we basically have a case where we have no overdispersion. On the left-hand side, we see that as x increases, we have larger variation. So despite the fact that we have the same underlying, same fitted curve, so to speak, the same kind of expectation, we have more variation for larger values of x. Here on the right-hand side, we have very, very small variation for large values of x. Okay, so depending on where we are in the spectrum, we can have more or less overdispersion, so to speak. Okay. And to the extent that this occurs in our data, we have to take that into account, and we cannot rely on the Poisson distribution, because the Poisson distribution makes the assumption that the variance is constant or is equal to the expectation. Okay. All right, so one way of kind of relaxing this assumption is, rather than using the Poisson distribution, is to just rely on the negative binomial distribution, and all that this negative binomial distribution or the negative binomial regression then does is introducing an additional parameter for potential overdispersion. So basically, we're estimating the variation separately from the expectation. Okay, so we're relaxing this assumption of the expectation being equal to the variance in the Poisson distribution. Okay. If we do this, in order to do this in Stan, all we have to do is we have our same model call. The only thing here is that we change the data distribution from a Poisson distribution to a negative binomial distribution. The link is still the same. Okay. If we don't want to rely on Stan, we can use a different package. Here we can use the mass package, for example. We could just load this package and then use the glm.nb command. I just directly called the function from this package using the two colons here. The command for the negative binomial from the mass package is glm.nb, and that directly assumes that this is a negative binomial distribution, so we don't need to include this family argument, and we can directly estimate this model. Okay. Again, you can compare the results if you like, if you go through the code in RStudio Cloud that is used for these slides. But essentially, what you will see is that, at least in this case, in this basically toy simulated data set, we didn't have any overdispersion. And so the results of the negative binomial distribution are essentially the same. We have an intercept of 1 and an x coefficient of 1.9, and we have this basically dispersion parameter that we're estimating now in addition. Okay, but since we simulated from a random normal, from a Poisson distribution, this assumption of equal variance and expectation was of course not violated. Okay, and therefore the results of the negative binomial and the Poisson are essentially the same in this case. Okay, if we want to two things I want to say about the interpretation of the coefficients. We'll talk more about visualizations and kind of going through a couple more exercises in our Q&A session. But in general, when we're trying to interpret both the coefficients for the Poisson regression as well as the negative binomial regression, the coefficient interpretation is basically equivalent to the coefficient interpretation of a linear regression, where the dependent variable or the outcome measure is logged. Okay, so remember in the linear regression case, with a logged outcome measure or logged dependent variable, we can interpret the coefficient as the percentage change in the outcome measure that is associated with a 1 unit increase in the predictor. Okay, so in other words, increasing our predictor by 1 unit increases the expected value of the dependent variable in our model by 2%, basically. Okay. Same for the negative binomial. It's the same interpretation, since we're basically modeling the expectation or the expectation using this log link. Okay, and therefore we have a similar interpretation to a linear regression model with a log dependent variable. Okay. The next thing is, how do we decide whether we need a negative binomial or a Poisson regression? There are some tests we can run from like kind of a frequentist perspective, but we can also use the methods that we already covered in previous weeks for linear regression and logistic regression to evaluate model fit. We can use graphical posterior predictive checking the same way we used it in previous sessions, and basically compare our actual observed data distribution against our posterior predictive distributions, okay, from a couple of draws from our posterior distribution. Okay, and if we have, for example, overdispersion and we run a Poisson model, and then we would see that basically the variation in the posterior predictive distribution, or the distribution of posterior predictions is more or less, or has less variance than in the actual data distribution. Okay, so you could directly kind of diagnose this issue of potential overdispersion in the posterior predictive checks. Okay, another thing we can do is, for example, use predictive checking with test statistics, the way we talked about also in the past. For example, one thing that we often encounter in count models is that we have a very large number of observations with just zero events. Okay. And in cases like that, what we need to do is we need to expand our model and use something that is called a zero inflated Poisson or zero inflated negative binomial, where we additionally take into account that a lot of observations basically just remain zero, and then we need to kind of separately from that model the number of events conditional on it not being zero. Okay. And so in order to evaluate whether we need to kind of expand this model and include this zero inflation aspect, we can, for example, check the test statistics where we just look at the proportion of zeros both in our actual data distribution and in our posterior predictive distribution. Okay, and so if in a case where the actual kind of observed test statistics is far outside of the range of basically the posterior predictive distribution for y being equal to 0, then we know, okay, maybe we have to include this zero inflation component in our model as well. Okay. But so much about count data. Again, we'll talk a little bit more about specific coding examples in the Q&A session, but I just wanted to give you a quick overview of kind of the basic commands. Okay. In the next video, we're going to talk about ordered categorical data.